Okay, continuing with the naming now of cycloalkenes, right? So cyclic alkenes, that means the cyclic structures with at least one single with one double bond. All right, now wherever the double bond is, that's always going to be carbon locations 1 and 2. All right, so you don't want to go this way because you want to give the positions 1 and 2 to the double bond. All right, so you want to go in this direction. So therefore the substituent now gets the location number 3, carbon number 3. All right, so it's going to be 3-methyl cyclopentene. You don't have to give the location of the double bond because in the cyclic alkene, locations 1 and 2 is always going to be the double bond. All right, so 3-methyl cyclopentene. Okay. Okay, it says name the following alkenes. It should be cycloalkenes and cycloalkynes. There's no cycloalkynes here, it's just cycloalkenes. Okay, so this is position 1 and 2. So there's 6 hexagon. All right, so this is going to be cyclohexene. Okay. Now here you have the double bond, this is a pentagon, so cyclopentene, and then on the third carbon you have 2 methyls. All right, so 3,3 dimethyl cyclopentene, cyclohexene, and then 3,3 dimethyl cyclopentene. All right, some links to environment. A lot of these odors that you associate, like roses, lavender, comes from these alkenes. Roses is this particular compound which has an alkene as well as, so it has 2 alkenes. All right. And then it has an alcohol functional group and so on. All right, okay, so a lot of fruits and plants, etc., synthesize a lot of these compounds that contribute to fragrance. They easily evaporate. Again, that volatility means, as you can see, if you spill some perfume, it easily evaporates. Okay. Cis-trans isomers, we're not going to look at it too closely here, but basically cis-trans isomers is that it's kind of like having a mirror images. All right, so if you look in the mirror, your right side is your left side and your left side is actually your right side, and so on. All right, so it's like if you place your 2 hands together, you can see their exact mirror images of each other. Okay. So now the cis hands is where you have the thumb sticking out in the same direction. The trans would be if one thumb is facing upward and the other would be facing downward, right? So that's what is called a cis-trans. When you have double bonds, the double bond fixes the atoms in space. All right, so if you have a substituent, if they have 2 substituents and they're both facing in the same direction, that would be called cis. If you have the substituents which are facing in opposite directions, then they would be called trans. Okay, so these are also referred to as geometric isomers. All right, because of the fact that that double bond creates a rigidity, and therefore the different groups that are attached to those carbons that make up the double bond, their spatial arrangement kind of gets fixed in space. All right, so if you have for example those the 2 chlorines, right? So now in this particular 1,1-dichloropropene, all right, okay, so there's 1, 2, 3. This is propene, 3 carbons. The double bond is between carbon 1 and 2. And at carbon 1, you have the 2 chlorines. So it's 1,1-dichloro propene. You don't have to give the location because it's just 3 carbons here. Okay. Now, this kind of compound cannot exhibit cis-trans isomerism because you have carbon with exactly the same groups, the same substituents. Okay. Now, suppose you had something like this. All right. You have butene. All right. So 1, 2, 3, 4. So that's bute. All right. So it's called 2-butene because the double bond is between carbons 2 and 3. All right. So in 2-butene, you can have cis-trans isomerism. So you'll take the last carbons as methyl groups, right? If those methyl groups are facing each other, and the 2 hydrogens are facing in the same direction, then that's a cis isomer, all right? Kind of like a boat shaped. Now, if those methyl groups are across from each other and the hydrogens are across from each other, kind of like in this chair kind of shape, okay, then it's going to be trans isomer, right? So this would be cis 2-butene, and this was going to be trans 2-butene, all right? So the carbons must have dissimilar groups attached to it across the double bond, all right? When you have similar groups, then you cannot have cis-trans isomerism. Okay. So the alkyl groups are on the same side of the double bond. In the trans, they are on opposite side, all right? So again, if you take 3-hexene, okay, it's possible to have cis-trans isomerism. If the hydrogens are, so this carbon, which has the double bond, has a hydrogen, and then this ethyl group, all right? So when the ethyl groups are on the same side, it's cis, all right? When they're across from each other, then it's trans, okay? All right, so pheromones are things that can either attract species or detect dangers and so on, warn the insects of dangers and things like that. Okay, so they are kind of chemical messengers. Okay, all right, so the sex pheromone produced by the female silkworm contains a cis double bond as well as a trans double bond. All right, so because of the cis trans configurations, placement of these cis and trans double bonds in the molecules, that's what makes them effective in their functioning as pheromones. All right, so the double bond is fixing things in space. All right, so this is trans, this is 1,2-dibromoethene, all right? So this carbon has a hydrogen here and a bromine. So the hydrogens are on the same sides, the bromines are the same, facing on the same sides, and so that's cis. And then when you have this kind of chair-like structure, then it's trans. Okay, name each using the cis or the trans prefixes. All right, the methyls on the same side, so that's cis. The methyls across from each other, that's trans. Again, the methyls on across from each other, that is trans. So cis 2,3-dichlorobutene, trans 2,3-dibromobutene, and trans 2-butene. Okay, the last part, this is the most important part, section 12.7, and here we are looking at functional groups, all right? Okay. So functional groups are a way that you can identify an organic compound, how they're going to behave, how you can predict what kind of behavior their physical, chemical properties are going to be like. So it's usually either a single atom or a group of atoms, all right? If it's a single atom, like a halo atom, all right? So chloro, bromo, all that, there could be just single atoms, all right? Or there could be a group of atoms, all right? Sometimes those groups are replacing a hydrogen in the corresponding alkane, all right? So this is one way to classify the organic compounds, okay? So table 11.9 is good at doing that, classifying all these organic compounds, okay? So you can see if you have a double bond, it's an alkene functional group. Triple bond, it's alkyne. And then you have aromatics. So alkanes, alkenes, alkynes come under the hydrocarbons, all right? If you have a carbon bonded to an OH group, like here, you have CH3, CH2, and one of the hydrogens, instead of ethane, one of the hydrogens is replaced by an OH group, all right? So this becomes ethanol, all right? And so that's an alcohol. Now, instead of the O, if you had an S there, because they're very similar, oxygen and sulfur are in the same group, so they behave kind of similarly, all right? So then instead of alcohol, it's called as a thiol because the presence of sulfur changes that prefix to thi, all right? So thiol, okay? So if it was OH, this would have been methanol, but it is SH. So it's thiol, methane, thiol, okay? And then if you have carbons on either side of an oxygen, like here, two carbons on either side of an oxygen, that's called as an ether. An aldehyde is where you have a carbon attached to a carbon with a double bonded O and a hydrogen. This can only be on an end carbon. You cannot have it in the middle, right? So that's called as an aldehyde. Now, if that hydrogen is replaced by a carbon group, a methyl group, all right? So you have a C double bond O right in the center, wedged in between two carbons. That's a ketone, okay? If the CH3 group was replaced with an OH, okay, that becomes an acid, right? Acetic acid would be, this is acetic acid, you have CH3, C double bond O, OH, okay? Now, if you replace this H with a carbon, all right, so it takes this form, C double bond O, O, and a CH3, that's called an ester, okay? Now, amines are derived from nitrogen, all right? So if you have instead of the three hydrogens, one of the hydrogens is replaced with a carbon group, that's an amine, okay? Amide is where you have a C double bond O and then an NH2 group. So a C double bond O and an NH2 group would be called an amide, okay? So alkenes, double bond, alkynes, triple bond, aromatics have this ring structure with alternating double and triple bonds, a hexagonal ring structure with alternating double and triple bonds. Okay. Alcohols have the OH functional group, OH. Thiols have the SH functional group. Ether has the O wedged in between two carbons. Aldehyde has a C double bond O and an H on the end carbon. Okay. If the H is replaced by a methyl group or a carbon group, then it becomes a ketone. Okay. If on the other hand, if instead of a methyl group you have an OH, all right, it becomes a carboxylic acid, all right, an organic acid. If that OH is if the H part of the OH is replaced with a methyl group or a carbon group, that becomes an ester. An amine is based from ammonia, all right? If you replace one of the hydrogens with a carbon group, that's called a primary amine. If you have two carbons and one H on the nitrogen, it's called a secondary amine. And if all the three hydrogens are replaced by carbon groups, it's called a tertiary amine. Amide contains a C double bond O and an NH2. All right, so the C double bond O, NH2, that's an amide. It's found in proteins. Okay, all right. Classify the following: alcohol, ether, amine, carboxylic acid, and ester. Okay. And that's the end.